Next on the agenda, we've got Leen Kalash from GSK. Leen obtained her PhD in computational chemistry and computer-aided drug design from the University of Cambridge in 2019. She then joined GSK as a postdoctoral research associate in data analytics and solid form informatics, which I'm pleased to say was a joint position with the CCDC. She performs in silico risk assessments of solid forms for GSK drug candidates and applies machine learning approaches to predict process relevant properties related to solid form, physical stability and processability. She's also been involved in data mining and analysing the GSK database of small molecule crystal structures and recently published a paper on this topic, which forms the basis of her talk today. Her talk's entitled The First Global Analysis of the GSK Database of Small Molecule Crystal Structures. Leen, over to you.
Good afternoon, everyone. Thanks, Rob, for the introduction and for giving me the opportunity to present today. As Rob mentioned, I have been involved in a database. The first database of small molecule crystal structures is a collaborative work with the CCDC, and it has been recently published in CRISP-EngCom journal. The paper has been featured on its back cover. This work aimed to increase our understanding of our in-house data in order to aid solid form design and to aid the choice of a solid form of an API that exhibits the properties and behavior of most suitable to produce a successful drug product. The GSK database is compared to the CSD drug subset, which is a public database in terms of crystal properties and diversity of solid form space. These features contribute to determining the safety, manufacturability, and bioavailability of the drug. So we have investigated the solid form distribution of the GSK database, and it was found that it is distinct from the CSD drug subset in its solid form distribution, particularly in the parent form, or what we refer here to as free drugs. So it is 58% in the GSK database versus 20% in the CSD drug subset. Also in the co-crystals, we have only 0.3% of our database to be co-crystals versus 31% in the CSD drug subset. So if we were to look at these trends and try to rationalize the reasons for this difference in distribution, we can think of the high candidate quality, which is received from medicinal chemists. Probably this has reduced the number of drugs in drug development requiring bioenhancement. This makes the parent form GSK's first option for development. We assess it, and if it is suitable, we go with it, and if not, we rather go to more complex options. Another reason that explains the bias in data, particularly in the parent or the free drug form and the co-crystals, is that in GSK, crystallographers usually collect structures to answer specific questions, which are mostly related to parent structures. And that's why we have a lot of parent structures in the database. As for co-crystals, why they are so low in our database, it's basically that co-crystals, it has never been GSK's first preference for development. On the top of that, once the structure is in the public domain, co-crystal studies from academic groups may increase the numbers in the CSD drug subset. We also looked at the space group distributions. So we looked at the space group profiles of the GSK database and the CSD drug subset. And the overall space group profiles of the GSK and the CSD drug subset are similar. But the GSK exhibits more of the space groups that support the packing of chiral markers. So this is basically attributed to two reasons. The first is that the medicinal chemistry approaches in GSK may have focused more on chiral molecules. And the other is that over the past 40 years, crystallographers usually collected structures to answer specific questions, many of which are related to chirality questions. We also investigated the relative Z prime distribution profiles for both databases, and it was shown that by far the most frequent structures are those with Z prime equal to 1 in both the GSK database and the CSD drug subset. So it's around 77.8% in our GSK database and 72.5% in the CSD drug subset. And we noticed also that there are far more structures containing symmetry of Z prime less than 1 in the CSD drug subset in comparison to the GSK database, particularly Z prime equal to 0.5. This constitutes around 12% of the CSD drug subset and only 2.4% of the GSK database. Closer inspection of these structures of Z prime equal to 0.5 and the CSD has shown that 98% of these structures have more than one distinct component in the asymmetric unit. So the high observation in the CSD drug subset is due to an artifact of high number of coformers that often straddle centers of symmetry, and how Z prime is defined in these cases. Also, if we look at Z prime equal to 2, the GSK database has around 17% of the database of this Z prime, and it's slightly higher than the CSD drug subset, which is around 12.5%. Both of these findings fit with the larger number of space groups that support chiral packing in GSK, since inversion symmetry in these are impossible, as chiral markers tend to mimic a centrosymmetric arrangement, and this requires 2 independent markers. Otherwise, the broad Z prime profiles are similar for both databases. We also looked at crystal descriptors, and particularly to assess the packing of crystals. So definitely that close packing is expected to lead to more energetically stable structures. And this feature can be assessed by looking at packing coefficients, which is the ratio of occupied volume out of the total cell volume in the crystal system. The packing distributions of these two databases are very similar, as shown, and they also agree well with those originally reported for aromatic molecules that range from 0.6 to 0.8 as packing coefficients. And also to gain a better understanding of GSK structures with low packing coefficients, we looked at the second plot, which represents the percentage void volume density distributions for both databases. It was around 9.4% of the CSD drug subset. It has a non-zero percentage void volume, whereas the GSK database has a higher percentage, around 15.4% of the structures. They have non-zero void percentage volume, which could be attributed to the fact that the CSD drug subset contains a larger proportion of marketed products. So in our database, we don't have only marketed products. We have intermediates and many other kinds of structures, not only marketed products. So given that the CSD, they have a higher proportion of marketed products, these drug substances have optimized solid state properties. The last plot in this slide is the hydrogen bonding pair distributions of the two databases. They were found to be very different. And the distribution of the CSD drug subset is shifted towards higher HTP values. This could be explained by the predominance of free drugs in our database. So as I showed you earlier, we have 58% of our database to be solid, to be free drugs or parent structures, in comparison to the CSD that has a fewer of these forms. And the CSD drug subset has more salts, so these are more capable of exhibiting hydrogen bonding interactions. And also the lack of co-crystals in our database may also have an impact here. Another interesting finding is that 22% or 23% of the structures in the GSK database, as we can see in the last plot to the right, they exhibit no hydrogen bonding, which is much higher than the CSD drug subset, which is only around 4.8 of the structures they display no hydrogen bonding. So in order to explain this more, we looked at some molecular descriptors in order to draw relations to these observed crystal descriptors. And it is shown in the log P plot that the increased percentage of GSK structures with no hydrogen bonding interactions in comparison to the CSD comes in line with the log-P distribution, where for the GSK database, it is shifted towards higher values, indicating that the molecules are more hydrophobic in nature in comparison to the CSD block subset. We also looked at some other molecular descriptors, which are molecular weight, flexibility, and branching density distribution for both of these databases. So flexibility is the number of rotatable bonds divided by the total number of bonds, which is a rotatable bond percentage for each database. And branching is the return of the number of walks of order 2 that start and end at the same atom, which is an indication of how much there is branching within a molecule. And we can see that the molecular weight and the extent of branching profiles for the GSK dataset are shifted towards higher values, which might contribute to the decreased values of packing coefficient distribution. Flexibility does not correlate with these observed trends, since the medians were not shown to differ significantly. Why we are looking at these descriptors? Because we refer to previous literature where it was reported that crystalline molecules tend to have low molecular weight and generally are simpler with lower number of rotatable bonds. On the contrary, uncrystallizable molecules tend to be more structurally complex and flexible, which makes them harder to crystallize. Also, in the literature, it was reported that the walk count or the branching descriptors are used in machine learning methods for the prediction of crystallizability of small organic molecules. Also, we looked at the morphology space in our database. So managed to apply machine learning on the GSK morphology data to predict needle formation of APIs. I'll explain this in a bit, but to start with, how does the GSK morphology data look like? So in GSK, first of all, there has been accurate recording of the morphology or the shape for many crystals, since they have been routinely case indexed. The morphology of the small molecule crystals captured in the GSK database was manually curated. So we looked at each entry and we did a curation for this data. So it was categorized into 1D, 2D, and 3D crystals based on the habit description of each entry in the database. It was found that in the GSK database, there is a higher proportion of 2D and 3D crystals with 38 and 39.9% respectively, as compared to 1D crystals, which constitute 21.8% of the GSK database. Why do we have less 1D crystals? This could be partly attributed to the fact that from an experimental point of view, they are generally harder to collect. So we aimed, this work was not part of the paper we published, so we extended the use of our morphology data to the application of AI/ML techniques, and we aim to publish this as a separate paper. So what did we do actually? We were aiming to relate molecular properties to crystal shape. So given that the molecules are the building blocks of a structure, so molecular properties would help in structure prediction, particularly in predicting needle-shaped crystals, and why we are interested in needle formation prediction, because this would serve as an early flag in property prediction, particularly in pool flow and handling properties. So what I've done is basically I've computed molecular properties for the 1D crystals and the non-1D crystals. These are the 2D and 3D crystals to train machine learning models for the prediction of needle formation. And this is a binary classification on whether a needle will be formed or not. And the trained models were tested on several test sets, including GSK and CSD drug subset as test sets, and they performed well with good accuracies. So based on molecular properties of an API, we aim to predict whether a needle would be formed or not. And the benefits of this predictor tool is that we can predict needle formation earlier in the pipeline before obtaining any crystal structure of an API. Also, we looked at polymorphic distributions in our database. So this is definitely to aim the risk assessments of solid forms of API drug candidates progressing to first time in human. So in GSK, we aim to deliver the most stable polymorph, and this constitutes a key milestone in our drug development process. But we hope that with the integration of data analytics we're doing here and computational studies, this would speed up the development process. So we investigated GSK polymorphic distributions, and it turned out that only 6% of the GSK database constitutes polymorphic structures. And this is basically due to the fact that, again, crystallographers usually collected structures to answer specific questions for experimentalists, and these were few and there were few related to polymorphic pairs. And definitely when they needed to collect two polymorphic pairs, it gets harder to grow these two crystals. So unless they are asked to do so, they would collect the structures. But at the moment, we have high interest in understanding polymorphic structures, and we aim to collect more polymorphs. So we looked also at one important parameter that contributes to the stability of polymorphs, which is their hydrogen bonding interactions. It was found that 48% of the polymorphs in the database have different hydrogen bonding interactions. That means either different interacting atoms or same interacting atoms with different coordination scores. So this is important because it constitutes the basis of the hydrogen bond propensity tool, which is the identification of possible polymorphs based on different hydrogen bonding pairs. Actually, we did look at the hydrogen bond propensity analysis of a polymorphic pair in the GSK database. And the tool shows that the more experimentally stable polymorph, which is the green circle in the plot, has a better mean hydrogen bond propensity value, as well as better mean coordination score. So as we look at the tables on the left-hand side, the upper table represents the more stable form where the donor donates once, and it has a higher probability than when it donates twice in the less stable form, which is in the bottom table. Also, the more stable form uses a better acceptor in the upper table, which is more likely to accept a hydrogen bond than in the less stable form, where it uses two acceptors that are much less likely to receive a hydrogen bond, as shown in the bottom table to the left. So in this hydrogen bond propensity model here, we used a combination of GSK training set and the CSD drug subset as a training set. And we obtained a good distinction between the experimental polymorphs. So the more stable polymorph had a better hydrogen bonding interaction. The same was the case when we used GSK training set alone. We had a good distinction, but that's not the case when we use CSD drug subset alone as a training set. Because in this case of polymorphs, didn't have a good representation of GSK functional groups. So this highlights the benefits of combining public and GSK training sets when building knowledge-based models of hydrogen bond propensity. And finally, this will take me to the conclusion slide. The data mining and the data analytics of the GSK database of small molecule crystal structures increased our understanding of the in-house data and how it can contribute to the future solid form design of pharmaceutical candidates for the benefits of patients. It was found that the CSD drug subset generally resembles the GSK database in terms of crystal properties, but not in the solid form space. We demonstrate the value in using hydrogen bond propensity tool to aid solid form design. We extend the use of the GSK data to the application of AI, ML techniques. Molecular properties were calculated for the 1D and the non-1D crystals, which are the 2D and 3D crystals, to train machine learning models for the prediction of needle formation, and we obtained good accuracies on different test sets. Future work will include leveraging the databases described here to predict process-driving properties such as solid form physical stability. And finally, I would like to acknowledge my manager, Nick Henley, and my GSK supervisors, Roy Copley and Cheryl Doherty, and all the people I worked with in GSK and the GSK Fellowship Program for funding. I would like to thank all the CCDC members I worked with. Either we worked together in a project or they mentored me. And I would like to thank you all for your attention.
Thanks very much, Leen. That was really interesting. Do please put your questions in the chat box. I'm more than happy to call on you, or if you want.
As an exponential growth.
But perhaps I'll kick off with a question firstly. I was really interested to see the number of structures that you have without hydrogen bonding interactions in the GSK database. And it got me thinking about once upon a time when I was a chemist, and there was a big explosion in kind of combinatorial chemistry, and lots of click chemistry and putting aromatic rings together. And that kind of approach made me think, well, maybe you wouldn't get too many hydrogen bonding interactions from that kind of chemistry. Have you considered doing kind of a temporal analysis of when some of these structures appeared in the database, and whether actually you've got a different looking portfolio now compared with back in the kind of 1990s, early 2000s?
So basically to track how the structure is different, differed in, with time. Yeah, that's a good idea. I can do this analysis. It would be interesting to do it, yeah.
Thanks very much. I've got a question from Bob Doherty. Bob, would you like to come off mute and ask the question, or would you like me to read it out?
Yeah, Rob, I'll come off mute if that's okay. Really, really nice presentation. I suppose one of the questions that comes to mind is, do you see a time when in GSK you will solve crystal structures for every candidate almost as a matter of routine? And how do you think that will change the nature of the database that you have, given that, as you said, a lot of the structures were solved to answer very specific questions?
Yeah. So basically, I mean, at the moment, as you can see, we did the first global analysis, and we are interested in integration of the data analytics. So we are at the start, and the reason why we have crystal structures in the database were so specific, as I mentioned, either to answer questions related to parent structures or chirality questions. They were so targeted. And even you can see it from the polymorphic distribution. We have a very low percentage of polymorphic distribution in our database. So definitely that would enormously change everything for us, because at the moment we are highly encouraging as much as we can collect, for example, polymorphic landscape, more structures that are related to the same family. Definitely it would help us, for example, in the solid form informatics. If we look at different properties of different polymers, we can learn from trying to draw out distinction between these polymorphs based on their different properties. We are highly encouraging it at the moment, and and no more answering specific questions. We are trying to collect as much structures as we can, because now we are at the start of doing the integration of data analytics.
Thank you.
Thanks, Leen. We've got a question from Alex in the chat. Would you like to come off mute, or I'm happy to read your question out if not?
Sure, yeah. I guess the previous question actually partially answered my question as well. So along the same lines about, you're going to be doing solid form screening, presumably, but only collecting a single crystal full structure solution on maybe your best form of that, and then wondering how, if you consider, all those additional forms that you likely have, I guess how that changes. And I was looking at also that number of about 6% polymorphic, and that seemed very low to me, but I guess that's just the data set that you have at this time, right?
It's basically data set over 40 years. So it's not representative at, for example, 2 years or 3 years. We have like over a spread of years, we collected like these polymorphic structures. Yeah.
Right. So I guess, as you were saying too, you're interested now in collecting more single crystal structures to get the full structure and investigate further, rather than just knowing that a compound is polymorphic, has different forms, but actually getting those structures. So that would be cool to see how that changes it over the coming years.
Yeah.
Yeah, great presentation. Thank you.
Thank you.
And just to wrap things up, Susan, would you like to add your comment to that?
Sure, maybe more of a question. Leen, thank you for a really great talk. I was going to add actually to Alex's question because I was thinking about the same thing. Should you add PXRD structures to the mix, or even electron diffraction structures for that matter? It's interesting to see the trends you're seeing with morphology, and I'm just wondering if you added powder structures or ED structures, if you would anticipate a shift in your morphology distribution to needles and plates, which tend to be more poorly grown.
I can't hear you very well, Susan. Can you please repeat your question?
So Susan's question is around the quality of structure you would expect to get if you added in powder pattern structures that you solve from powder patterns. Because
Okay.
would that change the balance then of needles and plates, because you're looking at different quality of structures in there too.
Yeah.
And you could extend that not just from powder patterns, but also to electron diffraction as well.
Yeah, so yeah, probably we will see another distribution. Yeah, we didn't consider this, so yeah, we'll try this too. Thank you.
All right, well, I think we're just about out of time for questions now, but Leen, thank you very much for your presentation. It was really interesting. I'm sure the audience agreed.